All right. Well, we are on the hour now, so I'll go ahead and kick us off. A few folks might be coming in as we move forward, but we'll let them kind of settle in. Before I hand you off to our fabulous presenter today, I did just want to do some quick housekeeping. First of all, thank you so much for joining us for Capacitors, Sound Waves, and Beats Lessons to Energize Your Classroom. We'll be chatting with Tom in just a moment, but first and foremost, the recording of this webinar will be available on our website over the next few days, and you'll receive an email with the recording link, as well as a folder with additional resources and a certificate of attendance. So keep an eye out for that. It may be early next week. We'd love to answer your questions during today's session, so please feel free to use the chat section in Zoom to ask your questions. Both Josh and I will be monitoring the chat. If we don't have an opportunity to get to your question, we will definitely follow up with you after the webinar. With that being said, I'll go ahead and pass you off to our presenters. Thanks again.
Thanks, Dylan. Tom Smith here. I'm part of the engineering and physics education teams here at Vernier. And I'll be leading the webinar today with the help of Josh. Josh, do you want to say hi?
Hi.
We both have similar roles, so if you run into some technical support questions, you may be talking to us on phone or chat or email. So I'll get started here in a second with a couple of demonstrations. We're going to be focusing on a capacitor lab that's part of our Physics with Vernier lab book, as well as sound waves and beats. And just looking at some tips for making those more approachable for your students this spring, and some ideas as to how you might implement those two labs. I'll start off with a bit of a confession. I was not a physics major when I was in college. I was an engineering major, chemical engineering specifically. And quite frankly, I went to school during an era when calculus-based physics was considered kind of the weeding out course for engineering students. If you could make it through calculus-based physics in reasonable shape, you were pretty much deemed eligible to move on into the professional school for engineering. That being said, it's not a great learning environment when you're just trying to survive a course. So when I got into the classroom, I was pretty much reteaching myself a lot of physics that I supposedly had learned some decades earlier. When I was teaching, basic electricity was pretty straightforward for me. But when I got to capacitors, I kind of took my time getting into it, and then went through the basics and rushed on to the next topic. Didn't spend a lot of time with it. And so I think that my experience is maybe not so unique as me being the only one in the world in that situation. So I'm going to offer some ideas about how we can make capacitors a little bit more tangible for students as we go through that lab. And then when we get to the sound waves and beats lab, I'll introduce that as an opportunity to perhaps flip your classroom and let the students take control of their own learning, and then you using your class time to do some checking for understanding and dive a little bit deeper into the topic. So that's kind of the plan of the day. I'll go ahead and start sharing my screen and talk about the resistor capacitor lab I have set up. So let's get that going here. Okay, so you should now be seeing a picture of our control, Vernier Circuit Board 2, the second model of it, along with graphical analysis set up there. And I'm going to suggest that for a resistor capacitor lab, it might be good to do a demonstration that allows students to visually see what's going on, rather than just relying on a voltage probe to give them some indication of what's happening. And then as we go through this a little bit, I'll also provide a bit more of a tangible example as to how students may relate to an RC circuit in particular. So on the circuit board, what I have, I'm actually going to be using, no, I forgot my power supply. Hang on just 1 second. So we have 3 options for power on the VCB2, the Vernier circuit board. I'm going to use this jack for the LabQuest power supply, just going to supply 5 volts of power to the circuit. And then we have the option of, batteries or another external power supply there. I have the power switch set to the batteries so that I'm not energizing the circuit at this point. In the circuit itself, we have a switch that allows me to alternate between where it would be charging up the capacitor from the power supply, or I can then isolate the power supply by flipping the switch and just running the circuit from the capacitor to the through the light bulb as my resistor. Now this is a fairly large capacitor. It's a 22,000 microfarad capacitor, and it allows you to visually observe an RC circuit a little bit more readily than the components on the circuit board. This is a relatively new product at Vernier, this larger capacitor. So I have that hooked up in my circuit now, and I'm just going to run through this a couple times. I'm going to charge it up. And if you keep your eye on this light bulb right here, you'll see, oh, well, I do need power to my circuit. So let's get the power switch in the right location. And then if I turn on the switch to energize the capacitor, it's now charged. And I can flip the switch again to discharge it, just isolating the circuit through the from the power supply. Take a look at bring my voltage probe into the story here. And for the circuit, we're going to actually, well, let me just do this one more time just to make a couple points. As we watch this come on, you'll see it flashes very brightly and then slowly dims. Both directions, both when I'm charging up the capacitor and when I discharge the capacitor. So I'm going to go ahead and get it charged up. I'm going to place my voltage probe across the capacitor so we can measure the capacitance or the voltage across that capacitor. And for this activity, I'm actually going to set up a data sharing event. So if you're at home and have graphical analysis on your computer or Chromebook, you're welcome to join in here. This is a data sharing over the internet is a pro feature. So the first thing I'm going to do is just share with you, if you don't have Graphical Analysis Pro, a temporary license so you can participate in that. To do that, I'm going to click on this distribute app link and copy that link. This is what you would do with your students as well if you were wanting to data share to your students' devices. So I can copy that link, just paste that into the chat. There we go, and you should be able to just click on that link in the chat, and that will be an active version of Graphical Analysis Pro. Now, I'm going to start a data sharing session, and I'll show you briefly how to connect to it so that you can get the data that I'm collecting at the same time. So I've started a data sharing session. This is the code that I'll copy that into the chat as well. And then I'll also make it large so that when I try to do this on my phone, I'll be able to see it. And I'm just going to demonstrate to you how you would. So I have graphical analysis pulled up on my computer, on my phone. I'm going to choose data sharing, not sensor data collection, but data sharing. And I'm going to, in this section right here, I'm just going to enter that code that shows up there. So it's XDW or YG. Hit connect. And I get an X and Y graph, just like I have on the computer there. When I connect my sensor to graphical analysis, that will show up there as well. So I'll go ahead and do that now. If you're trying to follow this along and have any questions about getting connected, just throw Josh a note in the chat. So at this point, I'm going to go ahead and start a new experiment. And I'm going to choose sensor data collection and make sure that my sensor is turned on. If I have a big list of sensors, I can use the filter using the serial number on the sensor, which ends in G5. So I just type that in and it isolates down to my sensor there. So put that in there. And I'll click, I'll point out at this point that I have both 1 volt and 20 volt channel. I'll leave it on the 20 volt channel for this experiment. Done. And I see on my phone that since I started a new experiment, it asked me if I want to join that new experiment, and I will do that. And then I'll see that on my phone, I have potential versus time, just like I have on my computer screen. This little green dot tells me I have data sharing activated. I'm also going to make the font a little bit bigger here so we can see it better. Okay, a lot of setup. There we are, ready to go. I'm going to speed up my sampling rate a bit and also increase the amount of time. I probably don't need to do that, but I'll go ahead and do it anyway. And I also want to set up triggering. This is how the lab is set up, and there's some value in setting up triggering. I'll explain that here in a second. So my voltage, when I just have the circuit set up, is about 5.2 volts. I want to start data collection as it's decreasing. I want to catch that exponential decay of the voltage as I release the charge from the capacitor. And I'm going to set that at about 5.1 volts, just to give me a little bit of headroom there to collect data. So now if I hit collect, it's going to sit there and wait for that voltage to drop. And I can simply come here and click across that line there. And you can see if I were to charge it back up again, we could see that charging and discharging again as well. So in this lab, we're really interested in that exponential decay that occurs for the voltage. And if I were to just highlight this first section here and click on this and choose apply curve fit and not a linear curve fit. That's not what we're looking for. We're looking for that natural exponent curve fit. And if we were to go ahead and apply that here, in this equation, so our voltage is equal to some constant times the exponent of negative cx plus b. This y value would be our initial voltage, and that c value is really what we're interested in. I'm going to change views for a second and just kind of sketch this out for us. So the basic equation we have for that exponential decay is that our voltage, which is a function of time, is equal to that initial voltage times the exponent of e to the negative t, that's our time, divided by RC, which is the time constant. RC is the resistance times the capacitance of that particular circuit. And if I think it's worth unpacking this a bit for your students rather than just providing them this equation and explaining that, this is the equation that dictates this exponential decay. And if we take a look kind of at this picture right here and focus on this idea right here, negative T over RC, and think about, the word time constant is a little misleading in some ways. Students may wonder, well, what does that mean? Is that when all the charge is dissipated, or what exactly is that referring to? And if we think about going out to a time that is equal to a time constant, we're driving this to a value of -1. And if we look at the value of e to the -1, that is approximately 0.37. So after the time equal to one time constant, where the voltage should be about 0.37 times our initial voltage. We actually have to go out 3 time constants. So erase that so I can capture this. If we go out to e to the -3, where we've gone 3 times this value of RC, we're going to get out to about 0.05, or having dissipated about 95% of the original voltage for the voltage on the capacitor. And it just follows that exponential decay function. So the other thing that you may or may want to spend some time with, kind of in this realm of discussion with your students, is just talking about the units of farads and what is, how does that make any sense at all? So a farad, it's defined as what, charge per voltage. I'm going to get that backwards if I'm not careful. And our resistance is in ohms, but that's also equal to voltage divided by current. And current could be rewritten as charge per unit time. So if we look at this RC value, that's going to give us voltage divided by charge divided by time times charge divided by voltage. And our units cancel out, so this gives us units of time as a time constant. And in that equation where we have -T over RC, that becomes a unitless quantity. So that just all kind of works out. Again, this is not very intuitive, so you might go back to the circuit a bit and think about what is going on in the resistor as the capacitor is being discharged, and recognize when you're discharging that capacitor, there's only 2 components in it. There's the capacitor and the resistor, and so their voltages have to be equal and opposite in order for Kirchhoff's laws or rules to be obeyed. So there's a bit of a more conceptual conversation you can have with your students at that stage. let's see, what else do I want to mention about that?
We do have a question in Q&A. Joanna is wondering, if you wanted to do this without a circuit board, could you use a capacitor in series with a large resistor with a small light bulb?
Absolutely, yeah, you don't need the circuit board, but you do need a power supply in order to charge up the circuit, charge up the capacitor, and then safely discharge it. So you would just want to pay attention to that combination of resistance and capacitance to make sure that it was balanced appropriately, so you're getting a good time constant that you could capture with the data collection tools. And I'll also mention that, we're using graphical analysis and our Go Direct sensors. These labs are certainly approachable from our other software and hardware options as well. Okay, let's, I guess one other point that I'll make while we're looking at this, let me just kind of zoom in here a little bit. And, these are the parameters of this equation. I'll note that there's a recently added tool of showing the uncertainty of the different fit parameters. So this just lets us take that C value, that time constant, the inverse of the time constant, and look at how closely that decay equation fits for that particular parameter. And in addition to the root mean square error that's provided for the entire fit. So it gives a little bit of confidence about how good that fit is relative to the time constant factor. Okay.
Do you want to take a moment to talk about the C fitting parameter and why we might in particular look at that one? Joanna and Chad is asking about the significance of each part, but I know you're going to clue in on, especially on that C parameter.
Right. The time constant is wrapped up in that C value that represents in the equations that I was putting up on the I can see if I can get this up here. If we look at that e to the negative t over RC, the t value is like the x in that equation, and this 1 over RC is the c value. So basically, that if you took that c value, which is something over 2 and some change, so we would expect our time constant to be about a half a second, in other words. So that's 1 over RC. And again, if you were setting your own capacitors and resistors up to run this experiment, you would want to pay attention to that. The large capacitor is nice because it just has 22,000 microfarad capacitance. So it's a fairly large capacitor, can partner with a small battery, or excuse me, light bulb from a flashlight to work pretty well. You have anything to add to that, Josh?
I don't think so. Yeah, you did a good job there. I think that combination of R and C is important to keep in mind for demonstrations like this, where you want to be able to really see that light come on and then fade out as it discharges. You really need a large value for R and C, and so that really big capacitor you're using is great for that. If you look at the lab as we've written it, it uses a resistor and a capacitor that are built onto that circuit board, and they're much smaller, and so you end up with a much smaller time constant as well. So small, in fact, that it's hard to observe it in real time. And so in that case, you really do have to rely on the sensors and the software to capture the charging and discharging.
Yeah, that's one of the reasons why I went to the light bulb is you could actually see that charge and discharge. But Josh is absolutely right. With the way the lab is written, the time constant is smaller, and so you actually speed up the data collection and capture data over a shorter period of time, which is one of the reasons why I set the triggering, which is what they do in the lab, in order to make sure I capture that discharge event and don't have to worry about timing when I discharge versus when I collect data. Okay, I'm going to stop data sharing at this point and shift over to the sound waves and beats, unless there's any other questions. Actually, I see something popping up in, well, there's a couple things I wanted to touch base on. So I'm looking at the chat. Let me just take a look at time constants, not a topic for physics C, analyze series. And so the circuit, we certainly have labs dealing with parallel and series and related circuits. And the circuit board has a variety of components, resistors. It does have capacitors, but you can certainly set these resistors up in parallel or series or a combination thereof. It has light bulbs that you can use to visualize that resistance. It also has a potentiometer, so you can alter the resistance manually. And again, the variety of power supplies that you can include in that. I did want to mention when I was talking about this whole idea of resistor-capacitor lab is it's not the most intuitive thing as to where that fits into our daily life. But what example I can leave you with is the idea of the delay feature on your windshield wipers. So that is in fact just a set of resistor-capacitor circuits that are triggered a little bit differently. It's actually triggered on the upswing as you're charging a capacitor. After it reaches a certain voltage, it will trigger the windshield wipers to activate. And when they've activated, it just goes through one cycle, comes back, and that capacitor has been discharged. And with a long enough, you can alter the resistor in that circuit so that you can make that delay shorter or longer and just go through that cycle again and again. So as you're twisting your windshield wiper delay, you can think about your RC circuits and adjusting that time constant. Okay, so let me shift over to talk about the sound waves and beats lab. So I'll just start a new experiment at this point. And as I mentioned earlier, this is a good example of, this was a really fun lab. I really liked going and doing sound in my classroom, where I'd invite my students to bring in their musical instruments or bring their singing voices, and we would spend a portion of our lab just looking at the different waveforms that different instruments provided, or some of my more talented singers could nail a sine wave, or they could put a lot of vibrato in their voice and come up with a totally different waveform. So we had a good time with it. And I think the idea of the lab just looking at a sine wave and looking at interpreting that sine wave to capture the frequency and amplitude and kind of driving that idea home was pretty approachable for my juniors and seniors in school. So what I might propose to you all is this is a good opportunity to go ahead and flip your classroom, where you're basically giving the students the tools to do the lab on their own, and then the next day come ready to learn a little bit more and discuss what they've learned. So to that end, I'm going to switch sensors. Hang there for a second. And in order to flip this around so that they are going to be the drivers of the experiment, I'll go ahead and disconnect the voltage probe. And instead of starting a new experiment with data collection, I'm going to start a new experiment with sample experiments. So you could assign your students this lab simply by providing them access to Graphical Analysis Pro. And you'll see a number of our, let me point this out. You can sort this by topic. So under physics, we have a number of our physics labs from our Physics with Vernier lab book built in here. And we'll go ahead and open up this first part of sound waves and beats and just take a look at what's present there. So in all the sample experiments, we've embedded a video with sample data that we've collected. In this case, we actually have 2 sample sets included. We'll just take a look at one to begin with. And the video, we can watch it just as it is. We can also turn on the audio. So in this case, that makes a certain amount of sense to hear what's going on. It's kind of a funny video. It's a piano keyboard on a keyboard. And that is the lab right there. So we use this small electronic keyboard as a great way of capturing a sine wave. And on that particular, it's a Casio keyboard that you probably can't buy anymore, but it gives a nice sine wave when you put it on the flute setting. So you might have that available to you. You can certainly do this with tuning forks, but they may take a little bit more finesse to get good data. Actually, it's easy to get overtones with tuning fork. At any rate, they can do this at home. Let me show you one other feature of this experiment file, this enable replay. It's not a great feature for this particular lab, but it actually synchronizes the video with data collection. So you'll notice we're really fast data collection. This whole experiment takes, 3/100ths of a second to accomplish. So, but in the lab, students would go about determining the period and then the frequency of that experiment using, you can highlight a number of waveforms, come down here and choose statistics, and you'll get the change in time. And you could count the number of peaks of the waveform to calculate the period, take the inverse of that to get the frequency of the tone. And you can also do a curve fit. Let me just close that for now. Apply a curve fit, and we'll apply a sine wave. And in this case, we're interested in this second component here, the B value, which is equal to 2 pi times the frequency. So if you think of the frequency as a cycle per second, and there are 2 pi radians per cycle, so the B value is, you take that divided by 2 pi in order to get the frequency, which, if you do the math here, is about 407 hertz, which should be equivalent to the G note. You can have your students confirm that. We do the same thing with another note, with the F note. And so they can do that same exercise and see the difference in frequency. And then in part 2 of this lab, I'll just open this up briefly. Again, we can filter by physics with Vernier. And open up part 2 of this particular lab. And here we have basically the same video, but what we have are 2 notes being played. Actually, the video includes, you can see when he's pressing down, there are 2 keys that are being pressed down there. And we get this beat function here and a series of questions in the lab about that. So what you might do from this, if students are doing this lab at home, is when they come to class the next day, maybe you set up a data sharing episode. So I'll do sensor data collection. I'll turn on a different camera here. So I have my sound sensor there. I can go ahead and choose my sound sensor to connect to it. Just going to use my default microphone channel again. And I have here a tuning fork, and I have this, so you can use a tuning fork. It is a little bit more challenging to collect data using a tuning fork. I'll just give it a try. Hey, that didn't turn out too bad at all. So there's one note. You might just have your students, now that you could set up another data sharing episode. So I can start a session now and capture that, put it in the chat. And then I can have the students in my classroom tell me what is the frequency of this waveform, give them some time to determine the frequency of that. And then I'll just go ahead and demonstrate this with the Casio as well. I'll put this up here. I want to make sure I'm set on flute. And then let's see, maybe this is the right note to choose. And then have them figure out the frequency of that, and maybe actually have them come to some sort of an estimate as to what the beat pattern between those 2 waveforms is going to look like. And I'll show you something that I did that takes a little bit of time, but was kind of interesting to play around with. I exported a CSV file of the data, and I just saved it to my desktop. Let me call this number 2 because I have number 1 saved specifically. So, and then what I did is I went into that file and I used this simple addition in a spreadsheet to add those 2 data sets together to get a combined waveform, to look at the interference pattern, constructive or destructive interference pattern between those 2 sound waves. And you could have them go through that activity and then go ahead and open that up. So I'm gonna open that file. I won't save this, but I'm gonna go here, and you'll notice that I'm looking for that particular file. It's on my desktop. It doesn't show up here because it's just looking for video graphical analysis or Vernier graphical analysis. I need to choose comma separated values. And there it is, my sound and beats activity. And then I can open that up and show that that combined data set of those first 2 data sets gives me this waveform, I can figure out the frequency of that as well. So this is, kind of an opportunity again to put the emphasis of the learning on the student, and then really do some deep checking for understanding back in the classroom, which I'm kind of excited about. And then some of the other things you can do with this is, we could look at, let me go back to new experiment. And I'm going to go back to one of the experiments here. It's a combined waveform. Oh, this only has a combined waveform. Of course it does. Well, let's go ahead and take a look at, we have the ability to look at the FFT for this particular set of data, which gives us a peak value that's pretty close to the peak value of the single form, so 410 hertz. If I would have been quicker, I would have moved over to, I still have time to do that. So let me take a bit more of your time here to look at the two waveforms. Experiments. We'll use the filter again. We'll go to this, the first part, where we have two waves, and we can see those two waves side by side now. And here, if I apply the FFT, we can see that we get the peaks for those two waveforms at 410 hertz and 371 hertz. We can see that peak FFT right there. And it's an opportunity to talk about frequency based evaluation versus a time-based evaluation of that data, and just give students some exposure to that idea. Let's see if there was anything else. I guess the other thing that if you had time to play around with, it would be to go back to the just choose one of these waveforms and look at that curve fit for a sine wave. And one of the things that I always found challenging to explain was the idea of this phase shift, this kind of C value in this equation, and how that relates to which direction the waveform is actually shifted on the graph. So this allows you the opportunity, if the students have done this lab and gained this knowledge before class, you can start to dive a little bit deeper into some of these nuances of sound waves, etc. I think that's I'm looking at my clock and we're pretty close to time. Those are the major features that I wanted to cover today. Are there any other questions in chat or from you all that we'd like to cover before we sign off today?
Tom, I just want to congratulate you on the sine wave you made from that tuning fork. Whenever I use a tuning fork, it never looks as beautiful as that sine wave did.
Yeah, I was hoping it was going to be an advertisement for the Casio keyboard, but it turns out that you can still get a good sine wave from a tuning fork. Thanks. Well, if there aren't any questions, appreciate you tuning in this evening, taking some time out of your day to join us. And if you have questions about the webinar or the material or any other physics related stuff, feel free to reach out to Josh or I or anybody in the physics group here at Vernier Science Education.